So we start with the next section, 5.2, and it's called diagonalization. I'm gonna, even in the syllabus, it's split over 2 sessions. I'm gonna take our time here because it's got a couple of things that we want to do. So I'm calling this part 1. Okay, for today I'm gonna do only this, and it has to. So diagonalization. Well, the word diagonal is there, and it refers to a diagonal matrix. And so I want to start with an example and then to explore what is this concept. Okay, so bear with me a bit with me when I work out this example. This is just to introduce the topic. Then I will give an example where how you actually solve this problem. Okay, so let's take a very simple example. So I'm going to start with 2 by 2 matrices. Is it 3, 0, 1, 4? And so from 5.1, in 5.1 we learned about the eigenvalues and eigenvectors. So let's start there. So I want to calculate what's the eigenvectors, basis for eigenvectors, eigenspaces here, what are the eigenvalues, etc. So what you do is remember step 1 is the characteristic equation. For 2 by 2s, this topic for 2 by 2s is very quick. The problems are very easy, so that's why I do the 2 by 2s. Okay, so remember this was what you do is you take your matrix and subtract lambda from the diagonal and put this equal to 0. The determinant I meant. Now this is a lower triangular matrix, and we know actually what the eigenvalues are. I don't have to do this because if I expand this, I get just the diagonal elements, right? 3 minus lambda times 4 minus lambda equals 0, and so the two solutions are lambda equals 3 and lambda equals 4. And we have seen this in general, right? If you have a diagonal matrix, then if you have a triangular matrix, the diagonal elements are its eigenvalues. Okay. So that was easy. So step 2, let's get the eigenspaces now, rather the basis for the eigenspaces. Well, so lambda is 3. So now we look at this matrix where we subtract 3 from the diagonal, right? It's in this matrix we put in lambda equals 3, the matrix then. So this means in the original matrix we subtract 3 from the diagonals to get 0, 0, 1, 1. Okay, so just to make sure that everybody knows what I'm drawing, and subtracting 3 and subtracting 3 here. Okay, that's where it comes from. Okay. Good, and so this one we now have to row reduce. Look at that, it's row reduced. Well, okay, it's not in echelon form because I have to switch the 2 rows, but then I'm done. Okay, let's do this quickly. So I have 1, 1, 0, 0. So this is my pivot. So this is the pivot variable. This is the pivot variable, and then we have one free variable. And we know that we need to have a free variable here because that's exactly what we are imposing with our characteristic equation, right? To determine the 0, so there is at least one non-zero solution. There is at least one free variable. Okay, so this now means that we can write, I'm going to use x and y's instead of x1 and x2. So this means that x, y, so x is the pivot variable in terms of the free variable. That means that I bring this to the other side there, right? This row means 1 times x plus 1 times y is equal to 0. So we see that x is negative y of course is just itself, and then we factor out y and we get minus 1, 1, and this is the basis. Okay, and now we do the same thing for lambda, the other one. Lambda is 4. So this time our matrix is, we subtract 4 from the diagonal, minus 1, 0, 1, 0. Okay, and also this is, well, okay, so what we need to do, well, first of all, we can switch the rows. Okay, so we switch row 1 and row 2. Oh, it's so little that I do it quickly here. So that's 1, 0, minus 1, 0. Or I could have multiplied the top row with minus 1. I just want to have a 1 in the top, and now I do the row operation. Row 2 is row 2 plus row 1 to get zeros, and we get, you see that eventually we get 1, 0, 0, 0. That is our reduced echelon form. And so what we have here, this is the pivot variable, and then the green, the other one, is the free variable again. Okay, so that means that x and y, this column is now, what is x? Well, 1 times x plus 0 times y is 0, so x is 0, and y is just itself. So we get y times 0, 1, and this is the other basis vector. So we have, this is the one for lambda is 3, this is for lambda is 4. Okay, so far everything is something that you recognize. So now I'm gonna, so as I said, for the next 5 minutes or so, I'm gonna play around a little bit to show you that actually some strange nice things happen. Okay, so what I'm gonna do is, first of all, I'm gonna make a matrix P. And this matrix is gonna be an important matrix that we're gonna always work with, the columns of which are gonna be the various bases that I get for every eigenvectors, for all the eigenspaces. So I had an eigenspace for lambda is 3, we had the basis this one, so I put this in my first column, and for lambda is 4, we got this column, this vector, so I put it there. So now by 2 by 2 there's only 2 choices, but if there are more, then we will see what we do there. Okay. You might say, which one goes first? Nice thing is that actually you have the freedom here. Of course, if you choose something else, you get a different matrix, but you can put 0, 1 first and then minus 1, 1, or that doesn't, both answers will be correct. Now, why do I do this? I want to calculate two products with this matrix P, and let me also write down what A was, because I'm getting out of screen here, 3, 0, 1, 4, right? 3, 0, 1, 4. Okay, and there's another matrix that I'm going to add, but I'll do that later. So let's first work out what is A times P. Okay, just humor me, that's why I want to calculate this. Times P, sorry. So times P minus 1, 1, 0, 1. Okay, so if I multiply this, remember, I hope you still know how to multiply, right? So you take this, no, that doesn't work. You take these two, multiply them, and then these two, multiply them, and add all this up, okay? So we get minus 3, right? And then you do this for the same, for this element, you do 3 times 0, 0 times 1, so the whole thing is 0. It's no surprise because we know if we multiply, both are upper triangular matrix here, lower triangular matrix, and we know the product is again will be lower triangular. Okay, so now this element that is minus 1 plus 4, that is 3, and then finally this element is 0 plus 4, so that is 4. Okay, we get this. Now I want to do, but look, actually something nice happened. Let's compare this row, this column, sorry, with the original column, right? This is our original column. What is this? Well, this is 3 times, right? 3 times the original one. And what about this one? I mean, it's 4 times this one. Okay, where does this 3 and 4 come from? 3 and 4, 3 and 4, 3 and 4. Okay, I'm telling you, I'm just showing you nice coincidences, and then we're going to really work that out. So I can express this, saying that that this new matrix is obtained from this matrix by multiplying the first column. So, okay, so we have this matrix here, right? So this is, wait, let me give myself a bit of space because I want to write something else. So this is the matrix P, minus 1, 1, 0, 1. And I now want to get a different way of saying, how can I get a matrix so that I take the matrix such that I get 3 times this column and 4 times that one. The trick is to multiply with this matrix. Okay? Let's just verify. Say that's the trick. Well, okay, let's verify. Let me get rid of these guys now. What do we get? Okay, this element, so find this element, it's minus 3 plus 0, okay. To find this element, it is 0 plus 0, okay. To find this element, it's 3 plus 1, that's 3. To find this element, it's 0 plus 4. The same thing, so they are the same, right? So what is this? So now, this was this is the matrix P, the first one is P. What is this matrix? Well, that's the new matrix that I want to introduce. That's the matrix 3, 0, 0, 4. Now you say, oh, I see, it's just you deleted one. No, 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 no. This matrix is the matrix that, this is first of all, this is first of all a diagonal matrix. Right? But remember, diagonal matrix is a matrix where only on the diagonal you have possibly non-zero elements. And what are the diagonal elements are exactly the eigenvalues. Okay, I'll do with an example where you have, with a different matrix, you'll see that it's that you cannot just guess what this D is, you have to calculate the eigenvalues. So this is D, right? So what I've now shown in my two calculations shows that if I multiply AP or I multiply PD, I get the same thing. So that means that A times P is equal to P times D. And I'm going to do one thing. First of all, it's not perhaps clear, but it will follow from the theory that P is an invertible matrix. So P is invertible. Well, it is clear actually. In this case, it's clear, right? Because remember, it's easy to see whether upper triangular or lower triangular matrices are invertible, because the determinant is just a product of the diagonal elements, and we see that the diagonal elements are all non-zero. So yes, this is an invertible matrix. So I can multiply both sides with P inverse. So I'm going to indicate this here. I'm going to multiply this with P inverse and this with P inverse. Of course, the whole reason that I do in front, because I have a choice. I can also do it in the back, I agree. But I want to do it in front because then these two cancel out. An inverse of the matrix times the matrix is the identity matrix. So I got to the formula that D is equal to P inverse AP. And what is this? What has this done for me? I started with the matrix A. I did a simple case because I took a triangular matrix, but we'll do it on an arbitrary matrix. And then I got, I did construct this P here, and then from that, if I calculate this new matrix, I get actually a diagonal matrix. So I made my original matrix diagonalization. That's where the term comes from. But of course, diagonalization, what does that mean? I know what the matrix is. That's the diagonal matrix, right? So, but the process in which I do this is a process that is important, namely, what we have done is we have changed the matrix by multiplying on either side of it with a matrix and its inverse. And that is an operation that we will call a similarity. So it's a term that is used in linear algebra often. So we say that how to say this? If P is an invertible matrix, but it has to be invertible, because otherwise it doesn't even make sense, then we say, then P minus 1 AP, this matrix is similar to A. So any matrix that we can obtain by multiplying at either side with P and its with an invertible matrix and an inverse gives us a matrix that is similar. Okay? So, in other words, what I have now therefore said is, what I have shown is that this matrix is similar to a diagonal matrix. Right? I said any matrix of this particular form here is similar to the original one, and so D is a matrix of that form, so D is similar to A. So D is a matrix, a diagonal matrix that is similar to A. So now the question is this always the case? And the answer is no. Now, I'm going to give you an example right away. So, therefore we have a definition. We say that the matrix A is diagonalizable, no, I'm getting here, diagonalizable, so mod full, right? Or can be diagonalized if it is similar to a diagonal matrix. Okay. In other words, if what I just did works. So you might say, what therefore can go wrong, right? Why can I not always do this? And I'll give you an example right away. But before I do this, I should, what is it that I wanted to say? Yeah, so, and the reason that we work on this problem is that it is no longer easy to check whether a matrix is diagonalizable or not. You can say, oh, invertible matrices perhaps. I don't know. They might not. And what about non-invertible? They might or they might not. So it is really nothing to do with the matrix and in other words, the determinant will not help us at all to decide whether a matrix is diagonalizable or not. We will give some conditions when it is, but it's actually a difficult problem, and we won't resolve the whole problem in this course. It's a high-level course to really look at all the possibilities, what can go on. But okay, I promised an example here, so I do another one here. So again, for simplicity, yeah, I should perhaps not have done that, but okay, I've chosen it now. I'll try later on another one. So I'll take again, this time triangular matrix again, but please, this has nothing to do, this should work for anything, right? So, and I'll do an example shortly with an arbitrary matrix. Okay, so here is A. So let's find the eigenvalues again and do the whole spiel, right? So step 1, the characteristic equation. That is, we subtract lambda from the diagonal and put it equal to 0. But perhaps you have by now also said, when I was doing it, you might say, but don't I know what the eigenvalues are? Yes, you know, because a triangular matrix, we know it's just the diagonal elements, and this is immediately clear from this determinant, because this is what you get. And this in particular, this is only one eigenvalue. You should find lambda is 1. That's the only eigenvalue. Okay, so step 2, what's the eigenspace? Now remember, what we do is we take A, so that the matrix that I'm writing down here is obtained from the original matrix by subtracting 1 from the diagonal, okay? Or if you want, putting lambda equals 1 in here. Okay, so this would be 0, -2, 0, 0. And then we have to write this in pivot form, which is extremely there, we're almost there. We have to just do row 1 minus a half row 1, so that we get 0, 1, 0, 0. This time our pivot variable is this guy, y, let's call it y, and then the other guy is the free. X is free. So if we write x and y in terms of the free variable, well, x is just itself, and what about y? Well, 0 times x plus y times 1 times y is 0, so y is 0. So x is 1, 0. So we have a basis vector 1, 0. Okay. So what was the next step that we did? Because we done, right? Because step 2 for lambda equals 1, but there is only one eigenvalue, so we are done. So what is now the problem? Notice the next thing I would have done was I would have made this matrix P by just putting in all the eigenvalues, all the bases that I have found that way. But of course, this has to be, to make it invertible, for one thing, it has to be a square matrix, it has to be 2 by 2 matrix. But I have only one column. I don't have the 2 columns. And that is reason why I cannot diagonalize this matrix, because I cannot form P. That's another thing that perhaps I should make clear is this P is, you have to take this P. Well, I said, except for one thing, you can choose the order in which you put the columns. You might say, what does that do then if I change the columns? So if you would switch these 2 columns here, right, you got a different P, true. And what is then changing? Well, this matrix will change. Then also the place where the eigenvectors, where the eigenvalues come, it will be switched. So you will have actually, so in the red case, so if you would have switched these 2 matrices, so let me write it, the red P would have been the choice this choice, right? And then the corresponding red D would be 4003. I should perhaps, that's perhaps a better way of saying it, because switching the rows is actually not exactly what happens here, right? The columns. So in other words, how do you go from, what is the connection between P and D? Again, next examples will make this clear. This was the eigenvector, sorry, I'll do it in the color. This was the eigenvector corresponding to eigenvalue 3. This is the eigenvector corresponding to eigenvalue 4. And that is why we got 3 there and 4 there. And if we switch them, you see we get exactly the opposite. Okay? But other than that, that's P. And I have no, but I cannot do it here. I have only one column. That's the reason why this doesn't work. Okay, let's do an example, a 2 by 2. Give me an example. Which stuff here I'm gonna take. Let's do this one. Sorry, where is it? Where is the one I want to do? Okay. So let's take the matrix minus 14. No, I don't want to do this one. Sorry, guys. Sorry, that's not what I wanted to do. Okay. I don't remember where I put the matrix that I wanted to do. Give me a sec. I'm gonna find it out right away. Where did it go? Where did it go? Here. Okay. Just a sec. Got it. Where is 5A? Ah, here it is. Sorry. Okay. 1, 4, 2, 3. Okay, that's the matrix. Sorry about that. Okay, so now let's start. So, okay, from now on onwards, this is how we're gonna do it. But everything else I've said, it was just leading up to it. Okay, so let me say the procedure. So how do we proceed here in the diagonalization procedure? Step 1 is, well, we need to find the eigenvalues. So the characteristic equation, that's still the same. Okay, so we have 1 minus lambda, 4, 2, 3 minus lambda equals 0. Now, we don't have a triangular matrix, so we don't know what the eigenvalues are. Okay, it's a 2 by 2, that's not so hard. 1 minus lambda times 3 minus lambda minus 8 is 0. Let's expand that, FOIL it out. 3 minus lambda minus 3 lambda plus lambda squared minus 8 equals 0. So lambda squared minus 4 lambda minus 5 equals 0. We need two values that multiply to -5 and add up to -4. So I think -5 and plus 1, right? Again, guys, you can stop this movie, right? And you can, each time that I do things, work it out. Work out the next step already. What's the next step? Well, now that I know what the eigenvalues are, lambda is 5 or lambda is -1, I'm going to do the basis for the eigenspace. So do it now and then compare. Okay, but I'm going to keep going. So I'm going to now have to plug in, so I'm doing lambda equals 5. Let's do that first. It doesn't matter which one you do first, but I'm doing this first. So this means lambda is 5. That's what I'm going to do here. So this would give me the matrix -4, 4, 2, -2. Okay. This is very easy, right? I can divide row 1 by -1/4. Then I get 1, 1, yeah. 1, -1, 2, -2. then I'm going to do row 2, replace that by row 2 minus 2 times row 1. Okay, so I get 1 minus 1, 0, 0, right? Okay, so we have our pivot, we are in row reduced form, reduced echelon form. So this is our pivot variable x, it's the pivot variable, and the other one y is the free variable. Okay, so we write xy as x minus y is 0, so x is equal to y, and y is equal to itself, so the eigenvector is 1, 1, or the basis for the eigenvector is 1, 1. That's lambda is 5. So what about lambda is, what was the other one? Negative 1. So now I plug in negative 1 in here, so lambda is now negative 1, so I get 2, 4, 2, 4. Okay, 2, 4, 2, 4. Okay. It's quick to do, but sorry, the next thing I do is row 1 divided by 2, right? So 1, 2, 2, 4, and then subtract from row 2 twice row 1. That's 2 times row 1 to get. You say 2 by 2 is very quickly, right? Perhaps I do a 3 by 3 today, or otherwise I do it next time. So we have, what am I doing? Yes, subtracting, so 1, 2, 0, 0. I know that this, if I don't get 0, 0 in the bottom here, then something went wrong, right? Because I would have 2 pivots, which is too much. I need a free variable. Okay, so here, this is the x is the pivot variable, and y is the free variable. Right, so what does this now mean? That x, y means that x is negative 2 times y, and y is just itself, so we have y negative 2, 1. Okay, that's step 2. We have a basis for eigenspaces. Step 3. That's the new step now, right? What is P? Well, it's very easy. P is just you take these two guys that you found, or whatever many that you find, and you put them in a matrix. So in this case, 1, 1, negative 2, 1. And you also declare what D is. What is D? Well, since I put the 1, 1 guy first, that means that which corresponds to lambda equals 5. That's the first one of my diagonal elements. And the next one will be then, this corresponds to eigenvalue negative 1, so I get 0, negative 1. That's it. So we have now D and we have P. Now remember, in the formula there's one more matrix, right? And that is this P inverse. So often I will ask you to do that. So step 4 is, well, we need still to find what is P inverse. Now for 2 by 2, again, this is not so difficult. Remember, we can use the formula for, we have seen all the way in the beginning a formula for it, which actually is just the adjoint. Okay, so what was that then? Remember, what you needed to do was, was it now? You switch the diagonal elements and change the sign of the off-diagonal elements, right? And then divide by the determinant. So it's 1 over the determinant of P. We still have to calculate that. And then what we get is we switch these two guys around, which doesn't mean a difference. And then we take negatives of the two other ones. So this one. And then what's the determinant? So the determinant of P, so that is 1, negative 2, 1, 1. That is 1 minus minus 2, so that is 3. So this would be for the matrix 1/3, 2/3, minus 1/3, 1/3. So let's now work out this product here. Remember this, let me write it up again. So the deal is now, so verify. With all this, we should have that D is equal to P inverse AP. Okay, let's verify this. I'm going to start, so I'm going to have to multiply out these things. Okay, so let's start with, So the question is this true, right? Do we have now what we want to say? So I'm going to start with multiplying these two guys out. I'll still write P inverse here. So A was, where did A go? Where did A? 1, 4, 2, 3. 1, 4, 2, 3 times P, and P was, where did P go? 1, negative 2. This nothing there. 1, negative 2, 1, 1. 1, negative 2, 1, 1. Okay, so what is that? So it's P inverse. I still have to do this. Well, let me, okay, I write it down already what P inverse is so that I don't have to copy it anymore. So this is, so okay, I'm going to work out this product and I'm just copying this guy. Okay, P inverse was 1/3, 2/3, minus 1/3, 1/3. Okay, and now we do A times P, so we multiply this out. What do we get? 1 plus 4, that's 5. And then we get minus 2 plus 4, that is 2. And I get 2 plus 3, that's 5. And I get minus 4 plus 3 is negative 1. Okay? And so now we work this out. We have 5/3 plus 10/3. Okay, what is it? Something is not right here, right? 5/3 plus, no, okay, no, wait. I'm doubting myself. 5/3 plus 2/3 plus 10/3 is 15/3, which is 5. Is that what I need? Is that the number in D? Where is my D? Ah, okay, that's already correct. So let's work out this one. That is 2/3 minus 2/3. Yay! Now this one. This is minus 5/3 plus 5/3. Yappy-dap. And then finally this one. Remember, it's this guy times that, right? In case you have forgotten, please go look that up. So this would be minus 2/3 minus 1/3, so minus 3/3. That is negative 1. Exactly the D that I wanted. So this is how you do this diagonalization. Okay, I'll take an example of a 3 by 3, and then there is more to be said. So I don't want to spend too much time on this, and I'll do this one here. Where is it? No, where did it go? Sorry, I'm in the wrong chapter. Not here. So A is the matrix 0, 0, negative 2, 1, 2, 1, 1, 0, 3. Okay. So let's work it out. Step 1. Characteristic equation. Okay, so we have to do determinant, subtract lambda from the diagonal, and copy all the other ones. I hope you see where this comes from, what I just wrote down. Okay. Try this. This gets tricky to find the determinants if it's more than a 2 by 2 because we have this extra lambda there, right? It's sometimes hard to get actually to make pivots and stuff like this. So you try to look for good expansions if possible, and I actually have one here. So I'm going to do here along column 2, this column there, because then first of all we know that the cofactor has a plus sign there. Should I check this? No. Okay, so we have this cofactor 2 minus lambda, and what is left then is this, right? So I repeat, the reason that I choose column 2 is because in general, I would have to take 0 times this element plus a cofactor, this element times its cofactor, this element times its cofactor, and add everything up. But since everything is 0 except for that middle guy, that's why I have only one term. That's why I consider even doing this. Okay, so what is left is minus lambda negative 2, 1, 3 minus lambda. Okay, that's a 2 by 2, so that one I just work out. So this is minus lambda 3 minus lambda, minus 2, so plus 2. So that is 2 minus lambda, and I have here minus 3 lambda plus lambda square plus 2, and now to factor the last one, so 2 minus lambda. So we need two elements that multiply. Okay, this is so I'm going to rewrite this underneath of here. 2 lambda square minus 3 lambda plus 2. Okay, that's the same thing, right? So I have to multiply to 2 and add up to negative 3. So lambda minus 1 and lambda minus 2, right? Yeah. Okay. So what are the eigenvalues now? Well, put this equal to 0 and you find lambda is 2. Put this equal to 0, find lambda is 1. Put this equal to 0, you get lambda is 2. Notice it looked like that these are two different factors, but they are actually the same except for the negative sign. So sometimes we would write this as lambda minus 1, lambda minus 2 squared, perhaps with a negative sign in front of it because of we switched the sign. So this is what we call higher multiplicity here. So that's why we have this lambda twice. Okay, but that's just something that can happen or not happen. So let's now do step 2, the eigenspaces. So eigenspace for, doesn't matter which one I do first, I'm going to do actually the hardest one first if you want, because there are 2 here now. Lambda is 2. Okay, so we replace lambda is 2 in our original, in this guy, so here. So we're going to do lambda is 2. So we get, I'm not going to be able to see this, can I? No, okay, so I'm going to have to, I have the matrix in front of me here, so I'm going to, so I'm subtracting 2 from the diagonal, so there would be negative 2, 0, negative 2, that would be a 1, 0, well, okay, sorry, you wouldn't see it, so perhaps it's, let me copy A again. So A was, I'm going to copy A here for, so that you can follow what I'm doing. 0, 0, negative 2, 1, 2, 1, 1, 0, 3. And so now I'm going to subtract 2 from there. So I do minus 2, minus 2, minus 2, right? So what I get is negative 2, 0, negative 2, 1, 0, 1, 1, 0, 1. There's a couple of things I can do. I'm going to make my life easy. Divide row 1 by a half. Now I get 1, minus a half. I said minus a half, right? 1, 0, 1, 1, 0, 1, 1, 0, 1. And of course now if I subtract row 1 from the 2 other guys, I get 0 rows there, right? And no surprise that this is happening, right? I told you, we need 3 variables. So 1, 0, 1, 0, 0, 0, 0, 0, 0. Now, let's analyze this. This is important. We have here the pivot variable, and there's only one pivot variable. So we have 2 free variables here. So this is free. So let's, and this is free. So this is x2, and this is x3. And this, let's call this x1. So this means that x1, x2, x3, what is this? There's only one equation here. It tells me that x1 is equal to negative x3, and x2 is just to itself, and x3 is equal to itself. We solve for, we factor out the terms with x2, that is only one of them, and then with x3 we have negative 1, 0, 1. So we have 2 basis factors here. So this is the basis for the eigenspace. And then there are 2. Okay? And that's good. That's the good news. So, but let me continue, and then lambda equals, what was the other one? Lambda equal 1, right? Okay, lambda equal 1. So now I have to subtract 1 from the diagonal. So I'll do this here. So now this minus 1, minus 1, minus 1, right? So what I get is negative 1, 0, negative 2, 0, 1, 1, 0, 0, 2. Okay? Oh, and look at that. Aren't they nice for us? No, that's something went wrong. What did I do? Subtract 2, 1, 1. Wait. Oh, wait, I mean, no. Something is not right? So subtract 1 from the diagonal. Negative 1, 0, negative 2. It had 1 here, I copied it wrong. Why was I worried? Because I have 3 pivots. That's not possible. I made a mistake. I know I have made a mistake because I cannot have 3 pivots. But I copied it wrong. Okay, this one I copied wrong. It had to be 1 here, right? There's a 1 here. And there's a 1 there too. Well, I copied everything wrong. My God. Okay, so let's get rid of this 2. So it is a 1 there and a 1 there. Yeah, so be, be very careful, right? I was trying to be smart here by not copying it, but I should have done it then. Okay, so that's the matrix. Yeah, I don't want to. I can replace row 1 by minus row 1 just to get a 1 there. I could have switched rows also, that's also possible. Okay, and now the row operation that I have to do, I have my pivot here, so row 2 minus row 1, and row 3 is also row 3 minus row 1. But this time, of course, I'm not going to get all 0 rows. I'm going to get 1, 0, 2, subtracting, so 0, 1, minus 1, and then I get 0, 0, 0. Okay. These are my pivots, and I'm in row echelon form, luckily, reduced echelon form. I don't have to do, normally this might not have been 0, so we would have to do something, but that's not necessary. So, yeah, this is our pivots, but we have a free variable, otherwise we would have been in trouble. Something had to be wrong then. Okay, so what does this now mean? This is x3, right? And then the other guys were x1 and x2. So, okay, this means that x1, x2, x3 is equal to, x1 is equal to, we read in this equation here, is equal to minus 2 times x3. From this equation, we see that x2 is equal to x3, and x3 is just itself. Be careful, right? I mean, people are tempted to write, oh, in this equation is 0. No, no, no. Free variables are always equal to themselves. It's only the pivot variables that we rewrite. So this doesn't play a role at all. Okay, and so there's only one x3 here that we can factor out, and we get negative 2, 1, 1. Okay, that's another basis factor. Now look, why are things will work here? Because we have these 2 guys, and we have this guy. Therefore we have 3, and now we can build P. So P, how do we build P? We put these 2 basis factors there, which correspond, by the way, to lambda equals 2. Okay. So okay, give me a little bit space here. So this is P, and this is D. I'll build D and P at the same time. How do I build P? I take the basis factors for the eigenspace corresponding to lambda is 2. And that was here 0, 1, 0. Okay, yeah. Okay, so these 2 guys, right? 0, 1, 0, and minus 1, 0, 1, minus 1, 0, 1. And that means this was 2. So that on the diagonal I get, for this one I get 2, and for this one I get 2, right? That's why we have twice 2 there. And then for lambda equals 1, the basis factor was this guy, so I put negative 2, 1, 1, that's P, and a 1 here, because that was the eigenvector. And the rest is all zeros, because this is a diagonal matrix. So this is P and this is T. So as I said, sometimes this is enough. I'm only asking to do this, but sometimes I would ask you to also find P inverse. And that would be through the technique of finding an inverse. The row reduction method is always the quickest method here. Now, it's getting a little bit late, so I don't want to do this in particular now, but I would try to do. So I'll say exercise, find P inverse, and then just calculate that P inverse A, P equals D. That's what should happen. Otherwise, we made a mistake. Okay? So, coming back now to this issue about when can we diagonalize and when not? Well, what could have gone wrong here is that if lambda is 1, okay, this eigenvector here, So notice, let's look at the eigenvectors. There are two types, right? This is the lambda equals 1 appears once, and that's good always. But this eigenvalue appeared twice, and then there is an issue here. Because what we need then is, because on our diagonal we'll have this twice there, right? The 2 will appear twice. So we need two eigenvectors. We need a basis consisting of two eigenvectors. The eigenspace, therefore, has to have dimension 2. Remember, the size of the base is the dimension. And this is the case here, but it's not always the case. Here is an example, all the way in the beginning, this one where we did, where is he? This guy here, it also had only one eigenvalue, right? But unfortunately, the eigenspace corresponding to this guy had dimension 1. So we don't, this was a root that, this lambda was twice a root, appeared twice as a factor in this characteristic polynomial. So we needed two basis vectors here, but we only had one. The dimension was only 1, it had to be 2. That's why we don't have enough to fill up to make a P. Here we are not in the situation. Here the P is a 3 by 3 matrix, so we need 3 columns. We always get one from each eigenvalue gives at least one column, because that's the definition of an eigenvalue. There is at least one eigenvector, so we can always use that one. But if one of these lambda occurs twice in this equation, then we need more. Then we need as many basis vectors. Okay, and so this is an example where it works, but there will be examples where it not work, and probably a homework problem, or next time we will see more of these examples. But I'm going to stop now, and this is already good enough to practice about this thing. And in the meantime, of course, it's a lot of practice also of finding eigenvalues and eigenvectors for the next quiz. Okay.